So as I have written in my email, today we are going to go through the written exam which was given on February the 4th, 2025. Okay? It dealt with reinforced concrete structure, which is the following. So the structure consists of a continuous beam with two spans. The restraints are fixed in and at the left, and two rollers. One is intermediate and the other is at the right end. Okay? The points were called clearly A, B, and C. So the first task, which was point A in the exam, is solve the structure by means of the two standard coefficients on the back of the page. Two standard coefficients are the coefficients for a simply supported beam subjected to a unit bending moment at one end. Okay, the coefficients are the two rotations at the two ends. Then you have the simply supported beam subjected to the distributed load, and the coefficients are the rotations at the two ends. So these are fairly commonly used coefficients. You know them very well from the course. They are well known with people who practice structural analysis. How to change this structure into something we can study by means of the coefficients available? Clearly this, if you look at it, is a continuous beam. It is, of course, statically indeterminate. If you look at it in another way, it's basically a cantilever which is fixed at the left end with two additional supports, B and C, which means structure is 2 times statically indeterminate, which means we have to solve for two unknowns. And as we repeatedly did during the course, the best choice in this type of structure is always to assume bending moments, be they at the one end or an intermediate bending moment, as static unknowns. Okay? Which basically implies you have to transform the structure like this. You change the fixed end in A as a hinge. You transform the first intermediate hinge as a full hinge, like this, interrupting the continuity, and everything else is left as it is. So changing the structure in this way, then of course the static load is still there, means my two unknowns are one bending moment here, call it x1, and an internal bending moment here at support B, call it x2. Note the difference between the two bending moments. One, the first, x1, is the moment which is exchanged between the structure and the ground. So on the structure there is just one curved arrow because we don't draw the opposite bending moment acting on the ground. We are not interested in looking at what happens on the ground in this exercise. In reality, we are always interested in what happens on the soil. Okay? This one, on the contrary, is an internal bending moment in the sense that it's the moment which is exchanged between the two spans AB and BC at point B. Therefore, to fulfill the principle of action and reaction, we draw two bending moments which have the same value, x2, that's why I wrote it all once. They are opposite in sign. In this way, the principle of action and reaction is respected. Okay? So how do we solve it now? Basically, we have to study the structure subjected to the different actions, and for the bending moments, we assume them to act with a unit value, to be consistent with the coefficients which are provided to solve the structure. So the first case you have to solve is the structure deprived of all the external loads, with only x1 acting and x1 with a unit value. So this is the situation. Now, if you look at the coefficients you have at the back of the page, with a unit bending moment applied at the left end, the deformed shape of the first span looks like this. There is a larger rotation to the left and a smaller rotation to the right. If you mark the rotations, their value is with a length L and the bending stiffness EJ. This rotation is L divided by 3EJ. Rotation at the first end. The rotation at the second end is half as much, L divided by 6EJ. Okay? By using my standard notation, the one which I use to indicate the coefficients when I solve statically indeterminate structure, this would be called delta 1,1. So the effect of unknown 1 at point 1, and this would be delta 2,1. So the effect on point 2 related to the statical unknown 1. Okay? Fairly easy, nothing to be worried of. Just realize that this shows how convenient it is to transform continuous beams like this, because basically what happens is that in this case, applying the bending moment here, nothing happens on the second span, shear force is 0, bending moment is 0, as is the actual force, because of course there is a roller over there. So if this structure, if this part of the structure is not subjected to any bending moment, there are no other effects, such as, for example, thermal deformations, which in this case are obviously 0, then no deformed shape, no rotation at point B. Now, x2 equal 1. Same structure deprived of all the loads, which means distributed load, nothing else. Then you have the bending moment x2, which is now 1, which means 1 on one side and 1 on the other side, not 1/2 and 1/2. Both are 1. To make the principle of action and reaction fulfilled. Okay? So the situation on the first span is the same as in the previous case, only the two rotations are in the opposite position, which means 2 here and 1 here. So this would be L divided by 6EJ. This would be L divided by 3EJ. And then we have the second span, which is again a simply supported beam. The only difference with the standard case that you have provided among the coefficients is that the length is not L, it is 3 divided by 2 L. So here we have 3 small arches, and the coefficient is 3 divided by 2L divided by 3EJ, because the bending stiffness is still EJ. This means 3 cancels out with 3, and the coefficient is L divided by 2EJ. Does it make sense to have this rotation, which is larger than this one? Clearly yes, because the stiffness of a beam reduces reduces as the length increases. So the longer the span, the larger the rotations, if the bending moment of line is the same. Okay? So, sorry, the coefficients clearly, in this case, this is delta 1, 2, and clearly it is equal to delta 2, 1. There should be always the symmetry requirement, so the effect of 1 on 2 is the same as the effect of 2 on 1. And then for the delta 2, 2, since we are looking at an internal bending moment, you know, you can either write that the rotation to the left is equal to the rotation to the right, or you can write that you can look at the relative rotation when you then write the compliance equation. We do it in the second way, so what we look at is the total relative rotation induced by this moment. As you see, the angle, which is initially 180 degrees centigrade, becomes larger because of both contributions. So the delta 2, 2 is then the sum of L divided by 3 EJ plus L divided by 2 EJ. And this is 5L divided by 6 EJ. Now the external load has not to be changed in terms of value, no unit value, we can use it as it is. So again, the structure, which is deprived of its continuity with the ground to the left and at point B, and we apply a load which is P, distributed load. So the deformed shape is exactly the one you find at the back of the page or in manuals. Standard case of simply support beam with a distributed load. Again, second span does not deform, it is unloaded. What we have is basically this, with an equal rotation at point A and at point B. This is P L to the power of 3 divided by 24 EJ. And the same happens here. And this basically means this is delta 1, 0. If you look at the sign, this rotation is clockwise, as were the previous ones, which were all positive. The same here, this rotation is counterclockwise, again, like the previous rotations, which were all positive. So this basically leads us to the core of the problem, which is to look at now the compliance equations. We know that in statically indeterminate structures, equilibrium equations are not enough. So to solve the problem, among all the possible equations which are in equilibrium, we choose the ones that are also respectful of compliance. What does it mean? We change the fixed end to a hinge, allowing rotations to take place. We change the internal support with continuity to an internal support without continuity. You see it very well here. There is a relative rotation between this span and this span, which cannot take place in reality because the beam is continuous. So the two compliance equations we are going to write will reinstate the compatibility. Okay? Basically making sure that these rotations which we allow to take place are 0. How are they written? Basically, x1 times delta 1, 1 plus x2 delta 1, 2 plus delta 1, 0 equals 0. First equation. x1 delta 2, 1 plus x2 delta to 2 plus delta to 0 equal 0. This is for point A, meaning the absolute rotation at this point, which is in contact with the ground, is 0. This is at point B. And careful, this doesn't mean the total rotation is 0. It means the relative rotation between left span and right span at point B is 0. So no kinks should take place. With the coefficients we have, these two equations reduce to L divided by 3j plus x2 L divided by 6ej plus PL to the power of 3 divided by 24ej equal 0. The second one is x1 L divided by 6ej plus x2 multiplied by 5L divided by 6ej plus PL to the power of 3 divided by 24ej equal 0. Okay? Compare all the coefficients with what we wrote before, and you will see that there is perfect coincidence. Now, how do we solve this system of equation? You have to be very careful because I see it a lot while I'm looking at the written exams. There are a lot of students which make mistakes because of calculations. So in solving the system of equations, I mean, if you can use the calculator. This is not a mathematics exam, so if you want to use the calculator, you can. If you solve it by hand, which is of course a possibility, the best way when the system is like this is to replace one of the two equations with a linear combination of the two. And by this, I mean that if you call this equation A and you call this equation B, whatever linear combination of these two equations can be added to the system. So, for example, a good idea is to do what? To do A minus 2B. Subtract this equation multiplied by 2 from this one. Because basically what you have is x1L divided by 3j minus x1 times 2L divided by 6ej, which is again L divided by 3ej. So these first two terms cancel out. Then you have x2. In first place, you have L divided by 6ej minus 2 multiplied by 5 divided by 6ej. So it's 10L divided by 6ej. I know this is 5 over 3. I leave it like that because it's more convenient. Plus 1 over 24 minus 2 times 1 over 24, which is 1 over 12. So this basically means that here we will have minus PL to the power of 3 divided by 12ej equal 0. If you replace here, what is the result of this? It's 1 minus 10, so it's minus 9 over 6EL over EJ, which is minus 3L over 2EJ. Okay? Okay, sorry, just one correction. This is, of course, 24 EJ. Okay. Now, the solving equation is x2 times minus 3L over 2EJ equal to PL to the power of 3 divided by 24 EJ. And then if you do the math, x2 is minus 2EJ divided by 3L times PL to the power of 3 divided by 24 EJ. The 2 cancels out with 24, which becomes 12. L goes away with L, which becomes to the square. EJ, EJ. The final result is minus PL squared divided by 3 times 12, which is 36. Okay? This is the value of x2. What can you do then? Well, you simply have to replace x2 either in one of the two starting equations. So, for example, equation 1. X1 will be equal to what? By reverting everything, 3EJ over L multiplied by minus x2 times L divided by 6EJ minus PL to the power of 3 divided by 24EJ. Okay? We do the math. 3EJ divided by L. Here you have PL squared divided by 36. Not EJ, sorry. Multiplied by L divided by 6EJ minus PL to the power of 3 divided by 24EJ is equal to 3EJ times L. This becomes 6 times 36 is basically 196. So what you have here is PL to the power of 3 divided by 196 EJ minus how many times is 24 in 196? Probably can't be done. No, so we have to do it directly. So this would be basically PL to the power of 3 divided by 24EJ. This would be equal to 1 over 196 minus 1 over 24. Again, there is something wrong. What did I do wrong? No, this is 216. Sorry. 216. So this would be 9 over 216. So the result would be 3 times minus 8 over 216. And the result in the end is minus PL squared divided by 9. Okay? Now to the second point, which read, determine the restraint forces at the four supports. A is a fixed end, so it has two reaction forces. And then we have B and C, which are rollers, so we have one reaction force each. In order to do that, it is better to break up the structure in the two spans and mark the unknowns which we just determined. So, at point A, we assume the bending moment to have tension at the bottom. We get a negative value, which is minus PL squared divided by 9. So we have to reverse it in order to put the tension at the top. At the second end, we have the same situation, only with a different value, which is PL squared divided by 36. We have to remember that this is an internal moment, so we have it to the left of point B, which is here, and to the right, in the opposite way. Here you have a distributed load, which is P. And what you have to find is the shear forces at the two ends. In my convention, when we have a span AB, I call this first shear force VAB, and this VBA. Same here, this is VBC, and this is VCB. So, in order to get VAB, the wisest choice is to write an equilibrium equation with respect to rotation about point B. In this way, we don't have the contribution of the unknown VBA. Okay? So, my first equilibrium to work out VAB is rotation about point B of the first span, AB. What do we have? We have, of course, VAB times L, whose rotation with respect to point B is clockwise. Also clockwise is this one, as you see. It's like a clock, so plus PL squared divided by 36. Then this first moment, which is counterclockwise, minus PL squared divided by 9. And the contribution of the distributed load, whose resultant is P times L, and which is applied at midspan, which means L divided by 2. So all together minus PL squared divided by 2 equal 0. In order to avoid mistakes, which I'm subjected to this morning, 1 over 2 plus 1 over 9 minus 1 over 36. So this is 7 over 12. Okay? In order to find VBA, the easiest way is to write the resultant of the forces in the vertical direction. So VBA is basically P times L minus VAB. So this would give us 5 over 12 PL. Okay? Then, what equation can we write to work out VBC? Again, since we have two unknowns on this span, the wisest choice is to write a rotation equilibrium with respect to C of span BC. Okay? This would give VBC times, careful with the length, because the length of this span is not L, it is 3 divided by 2L. Minus PL squared divided by 36, which is the bending moment at the right of support B. So BBC in the end is basically 136 times 2 over 3. The result would be PL divided by 54. As a consequence, VCB, which is this one, is equal to minus VBC, because in this case, there is no load applied on span BC, so the two shear forces at the end basically have to cancel out each other. So they are equal in value, opposite in sign. This means minus PL divided by 54. Okay? So what are the reaction forces now? At point A, it is fairly clear that one reaction force is VAB, and the other is the bending moment, x1, which we previously determined. Okay? Fixed end, two reaction forces, bending moment and the shear force. There would be also the actual, the horizontal reaction, but it is 0. At point B, you have to be careful because you have two shear forces. And this means what? This means that at the center support where you have the roller, and we have the reaction force VB. Look at here. The two shear forces VBA and VBC are both upwards. Their value is positive for VBA and for VBC. So basically what happens at support B is that you have downward forces from both sides. This is 5 divided by 12 PL, and this is PL divided by 54, which means basically VB in this case is VBA plus VBC. And the math, in order to avoid mistakes, (47) divided by 108 PL. At the right end, clearly, the reaction force is VCB, the only force which is acting there. Okay? So if I was to summarize the reaction forces in one simple scheme, in order to make it clear that I understood how things are, I would sketch them like this. This is A, this is B, and this is C. Here you have a reaction force which is like this. This is 7 divided by 12 PL plus a bending moment which is like this, which is PL squared divided by 9. At point B, I have 47 divided by 108 PL. Of course, here there is the distributed load applied, P. And here you have a reaction force which goes down, which is PL divided by 54. You can check it. These 4 reaction forces keep the structure in equilibrium under the applied load. Third point was plot the diagrams of the internal forces, clearly indicate the sign conventions, was the warning. Okay? So in our case, we have to plot the shear force, and I can plot it with only numbers by specifying that my scale is P over L, and my sign convention is typically shear force is positive, it is clockwise. This is what I mean by this small square with a plus, and 2 clockwise shear forces at the end. So again, we have first span, second span. Let's go back to the internal forces I previously determined. Here we have VAD at the left end of the beam. It's upwards. The value is 7 over 12 PL. My conventions are positive if on the left side it is upwards. So this 7 over 12 PL is positive. For the same reason, VBA, which is upwards on the right with a value of 5 over 12, is negative. So here you have to be careful. So divide this in 7. 1, 2, 3, 4, 5, 6, and 7, which means this is 5. Plot it in the scale. And then in the middle, how is the shear force going to be? With distributed load, the shear force is linear. From a positive value to a negative value, which means it's a straight line going like this. This is positive, this is negative. Here you write 5 over 12, and here 7 over 12. Note that we will need later on the point at which the shear force is 0. Where is this point located? If you have shear forces 7 over 12 and 5 over 12 summing up to 1, the ratio between these two lengths of the beam, which are divided by the 0 shear force point, is the same as the one of the shear force, basically meaning that this is 7 over 12 N. We will need it later on. What happens in the second span? VBC on the left of the beam is upwards. As you see there, it's, no, you don't see it anymore, but it was 54. Okay? This is downwards, as you see over there. You still see it here. Downwards on the right end. So this basically means that upwards to the left, downwards to the right, the shear force is positive all over span BC. It is constant with a plus here and 1 over 54 here. Why is the shear force discontinuous here? Why does it jump from a negative value to a positive value? As a matter of fact, if you look at this value, the distance between these 2 points, this is 47/108 PL, which is equal to what I call VB, concentrated reaction force. Always remember, where you have concentrated load applied, you see discontinuities in the shear force diagram. Do not make the mistake of putting discontinuities here where there is a distributed load. Okay? Not possible. Bending moment, I draw it in the scale PL square, and my convention is on the tension side. Why? Because in reinforced concrete sections where there is tension, I put reinforcement. Okay? So again, this is AB, this is BC. First bending moment is 1/9, and as you see, tension is at the top, as it happens at point B. So basically we have two moments, one is 1/9, the other is 1/36, so the ratio between the two is 4. I can start off with this one. Let's make it bigger. And then by taking this segment, 1, 2, 3, and 4, this is what I have at the first end. So my bending moment has 2 points here, like this. At this point here, where there is a roller, the bending moment is surely 0. There are no loads applied on the second span, so the bending moment will be either constant or linear. In our case, it is linear because it starts from a value which is different from the one where it ends. So basically, in the second span, we have something like this. Okay? Here, in the first span, as you know, when the distributed load is present, we have a bending moment diagram which is parabolic. 2 points are not enough to clearly identify a parabola. We need a third point, which is the wisest choice. Where the shear force is 0, we have a maximum bending moment, which will then be used for another task in the written exam. But generally speaking, when you have a span, it is always wise to know where the maximum bending moment is and what its value is. So basically, we had a point which is the maximum bending moment at 7 divided by 12L. So we know there will be a maximum bending moment here somewhere in the middle. How do we calculate it? Simply by looking at what happens on this portion of the beam. So I isolate this portion of the beam. I know there is a distributed load, which is P. I know the length of this segment, which is 7 divided by 12L. At the first point, you have a bending moment, which is PL squared divided by 9. And a shear force, which is 7 divided by 12L. What happens at this point where I do my cut? Of course, no shear force, it is 0. Just a bending moment, which is likely to be positive in the sense tension at the bottom. What is its value? You get it from writing the equilibrium for rotation about this point of this segment. M max plus PL squared divided by 9 plus PL squared divided by 2, which is, the contribution of the distributed load is P times 7 divided by 12L, which is the resultant, multiplied by 7 divided by 12L, multiplied by 1 divided by 2, which is the lever arm. And then you have the contribution of the shear force at the first end, which is negative, minus 7 divided by 12 PL multiplied by 7 divided by 12 L equal 0. The result, don't make me do all this math, I will present you with the final result, will be 17 divided by 288 PL squared. How much is it with respect to the other two moments? More or less half of the first moment. So I take this segment and I reduce it by this half. So the bending moment will be here, and the final diagram will be like this. Nice parabola with the values that are 1 over 9, 1 over 36. This is 17 divided by 288, located at 7 over 12. This is all I need in the solution of such a type of problem to know that you got all the numbers and the physical behavior right. Okay? Now, the fourth point of the first part of this practical application was calculate the rotation at the right support, point C, which is this one, clearly indicating its value as a function of PL and EJ, and sign clockwise or counterclockwise. Okay? In order to do that, we have to look at what happens under the different actions we have and that we already examined in the structural analysis part. That is why I redrew everything I had for the structural analysis part. Remember, these were the elementary cases I considered. Now, at point C, what is the rotation caused by x1? 0. Okay? What is the rotation at point C caused by x2? There is this contribution here, 4 arches. What would it be? It would be the value of x2, which in this case is 1, with the coefficient you have at the back of the page. Remembering that point C is not where the bending moment is applied, it's the other end. So putting this all together, this will be 3 divided by 2L divided by 6EJ equal to 3 divided by 6 is 1 over 2, L divided by 4EJ. Counterclockwise. As you see, it's counterclockwise. For x2 equal to 1. What is the rotation caused by the external load? Look here, 0. Summing this all together, I now choose the sign. I can either say rotation at C counterclockwise is equal to what? 0. x2 equal to 1, it's L over 4EJ counterclockwise, so in reality it will be x2 times L over 4EJ, and then 0 for the external load, so nothing. Now we replace x2. What is the value of x2? Value of x2, as we found it out previously, is minus PL squared divided by 36. Remember? You have it. You have it also here. It's minus tension at the top. So the value will be minus PL squared divided by 36 times L over 4EJ, which means minus PL to the power of 3 divided by 144EJ. What does it mean? That the counterclockwise rotation is negative? It means that the value is PL to the power of 3 divided by 144EJ, and the direction is clockwise. Again, I calculate the rotation assuming it is counterclockwise, and I get a negative value. So this means the value is this, and the direction of the sign is clockwise. It's more or less like with forces. You assume a sign upwards, downwards. Depending on the sign, you either keep the direction as you assumed it, or you change it. Okay? As a matter of fact, let's devote some additional minutes to check whether it makes sense. By looking at what? By looking at the deformed shape based on the bending moment diagram. So what we have is this bending moment diagram. Here we have a fixed end. Here we have a support, which means a fixed point. And here again we have a support. So this is a likely deformed shape here. Look at the bending moment diagram. Where you have tension at the top, it means curvature will be like this. Where you have tension at the bottom, it means curvature will be like this. And again, curvature will be like this where the bending moment is at the top. The bending moment tells us what the curvature is going to be. In the absence of other effects such as thermal curvatures, which we didn't cover during the course. But it is wise that you know that thermal deformations change scene. What is important is to look at the points where the bending moment is zero, because these will become contraflexure points in the deformed shape. So points where there is a change in the curvature. So starting from the undeformed shape, which I will likely mark here and dash it. What is a likely deformed shape? Remember that here there is a load, so this span is likely to sag downwards. Okay? We have to start with a no rotation and no displacement here, and then we have this curvature here. So starting point will be like this. Okay? Like a small cantilever. Then change of curvature, which means like this. No kinks in the deformed shape. Up to this point where there is contraflexion, which means again a change in curvature, and then a curvature like this all over the place, passing through point B, which is a support, and going to point C, which is again a support. As you see, this deformed shape is consistent with all the requirements I have, and as a matter of fact, you see a clockwise rotation, as it should be. Okay? So this basically ends the first part of the assignment, where we have to deal with the structural analysis part, and as you saw, it's all symbolic. Now, the second part starts, the design part. So, design and assessment. So there were some data given. L equal to 6 meters. P equal to 30 kilonewton over meter, and we specify that this is a load at ultimate limit state. FCD, design concrete strength, is 25 MPa, megapascals. And then we have FYD, which is the design yield strength of the reinforcing steel, which is 350 megapascals. And then we have B equal to 15 centimeters, and D equal to D prime equal to 35 centimeters. These are the data related to the typical reinforced concrete section, which has a width which is B, an effective depth D for the bottom reinforcement, and an effective depth D prime for the top reinforcement. Okay? In the sketch which was provided, the two sections with negative bending moment and positive bending moment were considered separately. I put them together in one drawing just for the sake of this. So the first point concerning the design read. Design the bottom longitudinal reinforcement at the point of maximum positive bending moment of span AB, assuming 12 mm diameter rebars. Typical design problem. So we have a section where we have a positive bending moment, which means tension is at the bottom, which means we are designing the bottom reinforcement, so we are interested in designing this one. We know the bending moment is 17 divided by 288 PL square. Now it's time to put in the numbers. So I will do the calculation for you. 17 over 288 times 30, which is the load, times 6 to the power of 2. The final result is 63.75 kilonewton meter. Careful with the units of measure. I have a load which is kilonewton over meter. I multiply by a length which is in meter to the power of 2. What I get is 63 over 63.75 meters. How do I work out the tension reinforcement? I don't know what the tension reinforcement is, so I cannot do calculation in an exact manner. I have to do an approximation. And the approximation, as you remember, is that this moment is resisted by a compression force and the tension force which is developed in the reinforcement, and the two have a distance which is represented by the internal lever arm, whose approximated value, this is Z. The approximated value is 0.9 D. What is D? D is 35 centimeters. So this internal lever arm is 0.9.35, 31.5 centimeters. Moreover, I have to assume that the reinforcement at the bottom develops its maximum capacity. So T will be equal to FYD times AS, where AS is the unknown we are looking for, so the amount of reinforcing steel at the bottom of the section. Putting this all together, we know that the resisting bending moment will be T times Z, which means FYD times AS times Z. By setting the resisting bending moment exactly equal to the acting bending moment, which is this one, we get what we need. So the minimum amount of area. So call this M max, maximum bending moment acting. The minimum area of steel is equal to what? Maximum bending moment divided by 0.9d, which is the z value, times fyd, equal to, careful with the units of measure. It would be nice to have something which is consistent from the point of units of measure. So we have maximum bending moment, which is in kilonewton meters. It is wise to put it in Newton millimeters by simply adding times 10 to the power of 6, because there are 1,000 newtons in 1 kilonewton, and there are 1,000 millimeters in 1 meter. 1,000 times 1,000 is 1 million. 0.9d, which is this value, 31.5 centimeters, has to be put in millimeters. So simply multiply it by 10. 31.5 times 10. And then we have the yield strength, which is FYD. It is given in megapascals, but you should remember that megapascals are Newton over square millimeters. So this is already consistent with what we have. So I will simply put here 350. The math gives us to the power of 6 divided by 315 times 350. The result is 578 square millimeters. Now this is not the final result, because I specified that the reinforcement consists of 12 millimeter diameter rebars. What is the area of a 12 millimeter rebar? A12, simply P times 12 to the power of 2 divided by 4. This is the area of one rebar. I should know it by heart at this point in my career, but I still don't. Better do the math. 113 how many rebars are 578 square millimeters? You divide this by this. So number of bars is equal to 578 divided by 113 equal to the result is 5.11. Do you round it up or do you round it down? Clearly, the higher the number of rebars, the higher is the bending moment. So to be on the safe side, this will be 5.11 rounded up to 6 phi 12. Okay? This indication means I need 6 12 millimeter rebars. Okay? Now, last but one point, check the top longitudinal reinforcement at section A, assuming it consists of 4 phi 20 rebars. And for this point, we have equations at the back of the page. Why? Because in an assessment problem where everything is known, we do not have to do approximations. We can work out the exact values, for example, of neutral axis depth and therefore of the internal lever arm, as it is specified at the back of the page. So our situation in this case is we are looking at section A, which is subjected to a negative bending moment, so we are interested in the top reinforcement. Okay? This value, remember, it's PL squared divided by 9. So this value here, the number, if you look at it, I already got it. It's basically 120 kilonewton meter. So the first thing we have to understand is what is the neutral axis depth, which means the area of concrete which is in compression. This is called neutral axis depth and its value is x. The equation at the back of the page tells us that the value is the following. FYB times AS divided by 0.8 times B times FCD equal to, careful again with the units of measure, yield strength is 350. AS is the area of 4 phi 20. So we know this reinforcement here is 4 phi 20. The value of the area of 4 phi 20 is simply P times 1257 more or less square millimeters. So multiplied by 1257 square millimeters divided by 0.8 is number, B 15 centimeters, which means 150 millimeters, and FCD is 25 megapascals, which we can leave as they are. So what we have in the end is this number of the area times 350 divided by 0.8 multiplied by 150 multiplied by 25. The value would be 147 millimeters. That's the neutral axis depth. Okay? Then we need, knowing that the tension is here, the distance between compression force and tension force. It's the internal lever arm. Z, again, the equation was provided. It's D minus 0,4x, which means D is the prime, I should say, 350 minus 0,4 times 147, and the value is 291 millimeters. Okay? Now the resisting moment, in this case, MRD is simply FYD times AS times Z. The result will be in Newton times millimeter. 350 is the yield strength times the area which is here, 1257 times 291. And I do the math again. The result is something like 128 millions. We divide by 1 million to get kilonewton meters. The result is 128 kilonewton meter. So since this value here is larger than this value here, which is the acting bending moment, check is okay. Now the last point of the assignment read, design the spacing of the stirrups required at the left of point B. Assuming the stirrups consist of two-legged vertical 8 mm diameter rebars. So this means that my section consists of such a situation. We have stirrups like this with 1 and 2 legs. Okay, this information is important. Why did I specify at the left of point B? Because if you look at the shear force diagram, you see that the shear force is different at the left and at the right of point B. Two different values. I specified there is a discontinuity here because of the presence of the reaction force. So which value should I take between 5/12 and 1/54 PL? This one. So the acting shear force is VBA equal to 5/12 PL, which is 5/12 times 30 times 6. The value is clearly 75 kilonewtons. How do we design the spacing of the stirrups? We have to remember that the resistance provided by stirrups, assuming Ritter-Lurch behavior, is given by the following equation. Z times FYD times ASW divided S, where Z is the internal lever arm, which we can approximate to 0.9D. FYD is the yield strength of the transverse reinforcement, which in this case is equal to the yield strength of the longitudinal reinforcement. This is the total area of the stirrups connecting the top and the bottom cord. So in our case, it's 2 legs multiplied by PSW divided by 4. So the area of 1/8 millimeter rebar multiplied by 2 because we have 2 legs. And this is the spacing which we have to design. So fair enough, to design the spacing, we need this equation. We simply need to invert this equation by making Z times FYD times ASW divided by the shear force applied in the point VA. What are the values? Z is 0.9D, so again 315 in millimeters times 350, which is the yield strength. Then you have to come up with the area ASW, which is the area of 2 8 millimeter rebars, so 2 times P divided by 4 times 8 to the power of 2. This is basically 100 square millimeters divided by, careful with the unit of measure, we are working in Newton and millimeters, so this 75 should become 75,000 because it's newtons, not kilonewtons. The result of this calculation, I will do it for you. The result is 147 millimeters. This is not a number which we can provide in a design. We have to round it. The question is, do we round it up or do we round it down? In this case, you have to remember that the smaller the stirrup spacing, the higher is the resisting shear. So when you get the value of spacing, you round it down, which means this is the maximum value of the spacing, which means that the spacing we will then provide is 14 centimeters. Okay? Remember this big difference with respect to the previous point? In bending, when we design the reinforcement, we round it up. When we design the stirrup spacing, we round down to be always on the safe side. Okay?